Hello reviewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about solar panel heat emission and its solution. So let's dive deep into it. So what exactly is the problem here? Well, first thing you have to understand scientific is that sun is the sole heat source, meaning if sun is dumping, let's say 1 kilowatt of energy per meter square, you're not going to add energy to it unless you are running a nuclear reactor or engine. And again, engine is still solar energy, but from the past. So sun is the sole heat source. So many times I've seen people exaggerating it, but trust me, sun is still the sole energy source. You cannot add energy. It's not like a chemical reaction that is giving off energy. So that's the whole point. Now, okay, we have sun dumping energy into it. We have atmosphere, so it buffers it out. So how hot something locally becomes, right? You have an atmosphere that buffers things out. But what about the exact on-spot temperature? That is affected largely by albedo, meaning how shiny that puppy is, meaning the shiniest thing we have is ice. Now you may think ice is cold because it's ice. Well, yes and no. Yes, that's a very big part. That is a 0 degrees Celsius, but again 0 degrees Celsius is not that low. And if you are in Western Hemisphere and Americans, you know, like 0 degrees Celsius, bruh, that's hot summer for us. So how the heck it goes so cold? Well, it reflects sunlight. So locally, that temperature drops a lot because sunlight cannot just penetrate. And ice has this ability to reflect almost 100%. Let me be very clear. 100% of solar photons is like yeet. It just yeets out of there. So locally, and again, it's why does it melt if it can do that? Yeah, that's why we said the atmosphere still buffers it out. So ice reflects, so ice is the coldest you can get. Second is forest. Most people are like, hey, forest is so cold, even in Africa, how the heck forest is cold? Well, forest is cheating, so to say. It's evaporating water away. Basically, it's like how beaver dams are so cool. Yeah, because they are evaporating water away. Like if you evaporate water, duh, it will be. It's like a desert cooler. So these are the two things that people generally associate with cold. One is cool because of evaporation, another is cool because of reflection, and two worst things are road. Road are like bad. Like road surface is bad. Not only it's bad in terms of albedo, but you also have to understand, just because you can see it and it may look, it's whitish, you have to understand you are looking at whole electromagnetic spectrum of the sun, the ultimate black body radiation. Yeah, at that point in time, you also have to look into IR, you have to look in ultraviolet, all of those things, and then you're like, yep, perfect black body. So road surfaces are brutally hot, and that's why your tire, even though it's exposed to the air that is hot, it's not melting, but the moment it goes into tarmac, it's like it starts to glue. That's the whole point. That puppy gets hot. That's bad. Like locally, that gets really bad. And solar panel is like that. However, let that be clear, there is one good thing about solar panels. They make electricity, meaning energy cannot be created nor destroyed. So if sun is dumping 1 kilowatt per meter square and you are leaching 10-20% of it away, that 20% is missing from the system. So fundamentally, it is not as bad. Like human buildings, human roads are bad. This is like, should have been better. So, but there is a problem of heat island effect with solar panels, because again, from albedo's point of view, it's not good. And how bad we are talking about? Well, one of my professor who is regularly consulted with basically solar farms, again, he's a structural engineer, and he said like they were talking about in certain places in February, when the air temperature is 30 degrees Celsius, the place just below the solar panel, and because it was a giant solar farm, was 50 degrees Celsius. So 20-degree delta was possible. So that's a problem. That's a road level problem. That's a serious problem. We must fix it. So how bad is the problem? Well, there are two aspects to it. First aspect that you and I all care about is money. That is, photovoltaic panels do not like it. Now, I have personal hatred towards Indian regulating bodies, ISI, because somehow Indian panels are rated for 25 degrees Celsius. I'm like, that's European temperature. India is hot. It should start at 50 degrees Celsius. Like we generally, I'm not even joking, our panels have rating of 25 degrees Celsius standard temperature. I'm like, what the hell? 50 degrees Celsius, 75 degrees Celsius, 100 degrees Celsius, that's how you have to rate. And look into any solar panel from any reputable manufacturer, all of them will give you this graph, and outcome will be the same in all of them, is that as it gets hotter, the output degrades. Meaning it's the same panel, like that's like 2 kilowatt panel is like, oh yeah, that 2 kilowatt panel is not going to give you 2 kilowatt. It's like, yeah, bro, I can barely give you 700 if it's very hot, which again, in India, it does get. So that's a genuine problem. And another aspect, if it's just like, okay, it reduces the power output, you will have larger panels, that's partial solution. You also have to understand it reduces the lifespan, meaning the cells that could have easily lasted for 25 years, like, bro, I got this, me good, it's like, bruh, I'm not gonna last, it's gonna poop itself and degrade very quickly, meaning the output will degrade faster even than this in just 10 years. So a panel that you were designing, and like, again, your business plan was, I'm going to replace this puppy, let's say 20 years down the line, you have to replace them 10 years down the line. So yeah, financially it is a problem that we must take care of, or bad things will happen. And it makes heat island effect worse, meaning if everybody in India starts to do that in a suburban kind of area, yeah, that puppy will start to get as hot as, like, large skyscraper buildings, because again, we'll increase the heat island effect. How bad that could be? From a city's point of view, or our research suggests around 3 to 10 degrees Celsius, or if you have a lot of roads, yeah, then it will be even hotter. So it does make heat island effect worse, so we must take care of it or mitigate it. And if we do not solve it, there are a lot of issues that are predicted down the line, which we must deal with before it becomes too bad of an issue. Because right now the smaller insects species cannot handle this, because again, a bee is far more affected by a regional spot of like 50 degrees Celsius air compared to a human can handle it, but a bee gets cooked. So bees, pollinators, small birds, yeah, they get cooked, like they get cooked by solar panels because of radiative heating, and it's bad. And we must just take care of it before it becomes really bad. So it is a bad problem and we must take care of it. So first line of defense is BandAid solutions. Now these will not solve the problem but mitigate it to some extent. First is mount it higher, meaning to maximize the land uses, we generally mount it as close to surface as possible. It helps in wind reduction and also basically wind loading, and also allows you to have lot of panels in same surface area, because again, you're not creating shading issue. Although that makes it worse, because again, that area becomes like you have a blanket of solar panel on it. It's bad. So increasing the height is the best thing we can do for least amount of cost. Now penalty is there that, hey, we cannot pack as many solar panels as possible, but you are not going to get that electrical energy if it was overcooking itself. So fundamentally is the least what you call harmful way of dealing with it. And again, once it's high enough, air starts to equalize. That's why I keep saying, you have to understand, sun is still the sole energy source. So it's not going to be like, okay, that whole area is going to cooked. So once you have enough airflow around it and it's not too close to the ground to act like a blanket, this mitigates it to some serious extent. Then we have secondary option, that is coating. Now coating is, you have to understand, if we had a supreme awesome technology, we do, but we cannot make it last outdoors. That's why we are not using it. Is we would have made what we call notch filter, meaning sun is emitting this much. We only have this much that we can utilize in our silicon. We'll put a band pass filter, meaning only this much photons get in, everything else get heat out of there. Our solar panels will be like, cool, bro. Chill, bro. Like you look at an infrared camera, it will look completely shiny. Look in ultraviolet camera, it completely shiny. Look in optical, it's like ultra black. So that's one option. Now, are people working on it? Yes. Last year when I was in a Scale conference, they really did showcase one of the coating technology that they have developed, finished developing. It acts like a optical fiber, it channels more photon and it causes cooling. I was like, how the heck you can put more photon and increase cooling? Well, it reduces stray reflection, that's the good part, meaning more photons going into it, and it reflects ultraviolet, meaning it heats ultraviolet. So it cools the panel by 3 to 5 degrees Celsius, so it does not get as hot. So that's one option. So you have mounted higher, put some coating on it, and then you can have active cooling. Now you can have some water sprayer cooling, or you can have fans, which is far more cost effective. Now you may be like, doesn't that leach energy away? Yes and no. Yes, it does physically take energy to run cooling fans, but you have to understand, if the solar cells are kept at 50 degrees Celsius, it's much better for them to be at 50 rather than be at 75. So if you drop the temperature from 75 to 50 by running forced air induction fans, you will find the energy that you are requiring for your cooling fans, it's coming from the increased efficiency. So your power output will not go up, but your cell lifespan will go up. So yeah, still economically viable plan to do active cooling. So that's one option. Another is just use better panels, because again, a panel that is 10% efficient will be very hot compared to a panel that is 20% efficient. And hopefully in future, humanity is going to bring down the space technology. So space technology goes up to tri-junction solar cells, that those puppy can touch 51%. Fundamentally, this is a heat pipe. If you can convert more photons into electrical useful energy, tada, less heating. So that would be the better solution, long-term solution, is that just have a better system, because again, more efficient, cooler it is. Another aspect, cleaning is also helpful. And again, in this regard, I'm genuinely happy that India has made some good progress, and a lot of our solar farms have cooling. And again, the cleaner you make it, the better yield it gives you, and also make sure the less heating happens. So these are BandAid solution. It does help, does allows you to. And again, for American audience, if you are putting things very close to the roof tiles, how about giving them some room? Or if you do not want to give them some room, have some air channels where you can circulate some fan. Some amount of circulation is much better than nothing. So these are BandAid solution that can take care of the situation right now. Now we come to the solution. Solution is PVT, photovoltaic thermal panels, meaning you get these two puppies married together. So you have photovoltaics and solar thermal panels, and you make love to them. So what kind of energy we are looking at? Well, in simplest, like, back of the envelope calculation, if 1 kilowatt is the electrical output, you're gonna get 2 kilowatts of thermal energy out of it. So yeah, that's why I said sun has more than enough energy. We just cannot extract all of it. Meaning, if you look at the sun's radiation output, bonkers amount of energy is there. If humanity can extract all of it, ooh, global warming, what was that? What was that? So the idea is, that's the closest we can get with photovoltaic thermal. Basically, electricity, heat, thermal, heat. So what about of energy we lost? Surprisingly little. So this is the best option we have right now. Now, at this point in time, if you are in European Union or in America or even Canada, you can buy this. Like, this is a common product. Yeah, they are expensive, but they are becoming more and more common. So you can just pick up a phone, and at least 3 to 5 vendors are there where like, I got you, fam. So in EU, they can do it. Now, why in EU and America? Well, they're cold. Like, they know cold. I know heat. So they're like, hey, we can heat your water. They're like, awesome, we need that in summer. I always find that weird. Like, again, from an Indian point of view, it's like, why do you need hot water all the time? Oh, it's like, your summer is my freezing cold. So for them, it's like, shut up, take money, take it and go, done, go home. And there's another aspect. You may think, wouldn't it be better to have 2 separates? No, this is a simple calculation. So let's assume you have fixed roof surface area. Duh, all things are fixed. So you would dedicate certain amount for your photovoltaics and certain amount for solar thermals. And what is the total output annually? Annually, you are going to get 22 megawatt thermal and 2.5 megawatt electrical. Not bad, not bad. But here's the deal. What if it's photovoltaic thermal? 22 megawatts still and 5.8. So you increase the electrical. Thermal, now is like, why wouldn't thermal went down? Well, you are still leaching some away. 100% is not 100%. You're leaching some away. And how it manifest is, basically, think in this way. Heat flux is the amps and temperature is the voltage. So you have a lot of amps. You just don't have enough voltage. So the reason why thermal did not went up is because temperature was low. So temperature wise, dedicated solar thermal collector will have higher temperature, but when you have PVT, the temperature will not be high, but the amount will be more or less the same. And especially if you increase the surface area. So instead of this much, you get more energy. It's just that lower voltage, more amps, kilowatt is the same. So right now, there is a lot of awesome solutions available, multiple brands, multiple different design, multiple topologies, some even vacuum sealed, which are even more efficient. So there's a lot of option for solar thermal systems, so PVT in Europe. Now, what about Indians? Yeah, this is where it sucks for us. It's like, what the hell are we gonna do with hot water in India? Our water tanks are hot already. And I'm not even joking, my water tanks can easily reach 35 degrees Celsius water directly. So it's bad. So what can we do with heat? Now, again, there are certain people who are importing these cells or making them themselves, simply because in hotels, hospitals, these sort of places, they consume a lot of hot water for certain tasks, laundry task and all that. So for them, it's like, yeah, shut up, take money right now. Okay, but what about Indian households? We do not need that much hot water. In those sort of scenario, there is one technology, ta-da, which we call absorption chiller. Now you have to understand, before we had compressor, we had absorption chiller. Basically, we used to use heat to do work rather than a compressor doing the work. Electrical energy doing the work, we used to have heat energy. Like, wait a minute, does that mean we can use fire to make refrigeration? Yeah. If you are in RV scene, you must have seen people using propane to run refrigerator. It's an old technology, like older than compressor. It's like, wait a minute, Then why don't we use it? Well, we do. We have been constantly using them. The problem is the COP, coefficient of performance, is low, meaning at good day, really good day, you're going to achieve 0.5. Meaning if you dump 1 kilowatt of thermal energy in terms of heat, you're only going to get cooling of 0.5 kilowatt. Now contrast that to AC. This AC puppy can easily in good scenarios can give you up to 3x, meaning 3 COP. So you're going to put 1 kilowatt of electrical energy, outcome would be 3 kilowatt of cooling. That's why we go with that. And so why do we use it still? Well, we still use it whenever we have waste heat. For example, a coal power plant, lot of waste heat sources, take it and go. You are running refrigeration for free, shut up, take money. That's why whenever you pick up a phone and ask for absorption chiller, generally they will say, yeah, we have 500 ton unit or 1 kiloton unit, 10 kiloton unit. I'm not even joking. Like, they do not go small. Like, this is the one very specific model that is very small, super small, of 11 kilowatt. Almost everything else is like, oh yeah, 500 ton. So we have to use absorption chiller, same size, 11 kilowatt. That's okay size for household. And then run it to basically two things. First, they can work at very low temperature. This is silicon absorption chiller. These can work as low as 50 degrees Celsius hot water temperature. But again, that's marketing data. I'm missing the cooling water data. So you have a cooling loop, so to say. That is where your waste heat is going. Then you have working heat. That is your prime mover. And then you have chilled water, which is the cooled part. So in this full data sheet, they have, if you give 90 degrees Celsius hot water, and your cooling tower water, and again, cooling tower does not mean like nuclear reactor cooling tower, it's a small thing, 29 degrees Celsius water, you should be able to achieve 7 degrees Celsius water. Now, is 7 degrees Celsius enough? While if you are coming from a refrigeration side, you may think 7, isn't that useless? Well, for a refrigerant, yeah. For water, no. Like, if you have 10 degrees Celsius water, it can still leach off more than enough humidity. If you're running fan and it's a dry environment, you're gonna freeze. Water has a lot of thermal capacity, so it does not need to be very, very, very cold. So 7 degrees Celsius there. Now again, the problem in India is that T delta between cooling water temperature and hot heat source will not be very high. So here the design is almost a 60-degree gap, and I do not think we can give 60-degree gap with PVT systems. So it will have effect. Now, there are two places where it can have effect. First effect is the coefficient of performance drops, but we have so much waste heat, that's not typically. Another is chilled water temperature will go up, and we do not need cold water as long as we can have human body temperature water, meaning 20 degrees Celsius water is good enough. We do not need 7 degrees Celsius. Or my approach is cascading refrigeration, meaning we run a refrigerator, normal air compressor, and then the condenser, after it tries to dump energy into atmosphere, it still is hot, use this at that point in time, then cascading. And yes, that is a common system, has been done in industrial scale, that does allow you to have very high COP. So that way we can use the waste heat even with 0.5 COP. So let's say 10 kilowatt electrical system, you still have 5 kilowatt of thermal cooling. That is a lot. 5 kilowatt directly adding to your refrigerators or basically air conditioner is significant. So it will dump as much kilowatt as it can dump in atmosphere. After that, it's like, I got you. This is like, I got you. So this is the only option Indians can do, where it's like, I got this. And again, Australians also. One of my friend is there, he says, that puppy gets hot. And for some reason, you have a lot of ultraviolet. Now we come to the realistic part of it. Physics, engineering, economics. Now physics part, I'm damn sure it will work. Question is how efficiently. Now, economics is the main daddy part, meaning if the machine is more expensive than the, like, you know, it will be buying other system, people will not buy it. So those parts play a role, physics, engineering, economics. But here's the reality of it. PVT is mandatory, as if our temperatures keep going up, solar panels will start to fry themselves. So we have to go to PVT. And here's the, when you leach energy, thermal energy away, it cools them down. That's why it's a good thing to do. So if we can keep them at 50 degrees Celsius for years, that's good, rather than like, oh, 70, 80, 90 degrees Celsius. Yeah, that's not a good thing. So fundamentally, if we do not do PVT very soon, like 3 to 5 years time frame, we'll start to reach a point where it's like, hey, solar panels are dying out, solar technology is dying out. And I have no idea what to do with solar farm. And because here's the deal, solar farms are in the middle of nowhere. So what the hell you were going to do with heat or cold? It's like that, I do not know. Now you're like, if we have heat, can't we use some sort of thermal energy conversion? Yes, you can use organic Rankine cycle, ORC. But problem is its efficiency is low. That's why we don't use it in coal power plants. That puppy only gives you 10%. So 1 gigawatt electrical output means 2 gigawatt of thermal output means 10% of 2 gigawatt would be converted into electricity. I'm not even sure whether it will justify the cost. So that's the issue part. But there is a lot of option. And again, we have to get into it. So thankfully, problem is there. And even better, we have solutions for it. We just have to optimize for it. So this was my presentation for basically solar thermal emissions and what we can do about it. So hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.